Hi, and welcome to Module 12 of Lecture 2. In this module, we're going to finish up the new material in Lecture 2 by discussing goodness of fit, how well our model captures the real life, how well our model captures the real causal interactions between X and Y. So, to get at that, we're going to talk more about prediction. Now, we saw before that our regression model allows us to predict values of the dependent variable from values of the independent variable. And this prediction will in general be better than just using the dependent variable. The first pass for the prediction for any prediction would be the mean of the sample. So y bar would be the first pass model of how to predict y, but it's not a very good one. By adding x and having the whole model y equals alpha plus beta x, we do a better job once we fit alpha and beta to the data. We do a better job of predicting y from x. And these predictions lie along the best fit line. Now, prediction isn't normally our goal, right? We can do a good job of hypothesis testing in theory, even if we don't predict very well, because all we're trying to do in hypothesis testing is doing a very weak test to see whether or not the coefficient on the x, on the independent variable, is different from 0. We can find that it's different from 0 because there's a relationship between x and y, even if the relationship accounts for very little of how y varies, as therefore not very useful for prediction. Now, I'm going to argue about that, but I'll leave that aside for now and move on to discussing more about goodness of fit, because we do sometimes want to know how well, despite that focus on hypothesis testing, we do sometimes want to know how well we do at capturing variation in our dependent variable. And we can do that by considering the concept of residuals, which are errors in prediction. So now we had before our estimates of alpha and beta, alpha hat and beta hat, and we have each of our points in our sample x sub I. Rather than considering the true values of yi, we can consider y hat I, which are the predicted values of y given a value of x and our estimates for the slope and y-intercept of our line. These predicted values y hat I will all lie along the best fit line. And it'll be our best predictions given our model of the value of the dependent variable given a particular value of our independent variable and the line itself that we calculated from our data. As we saw before, these predictions will not be perfect. There'll be some error associated with each prediction. They won't all lie on the line. The true values won't all lie on the line in general. This difference between the true value and the predicted value, we're going to call u hat. And there's one u hat for each data point I. And these u hats, these errors in prediction, are the residuals associated with the model. So let's go back to an earlier example, but we're going to flip the hypothesis here, and we're going to say that states with governments that employ more workers will have lower per capita incomes. So per capita income is the y, and government employees is the x. Here's the data from before. Here's a picture from before. Now the pictures actually make more sense given the flipped hypothesis. The x-axis is the independent variable of percent government employees. The y is per capita income. We have a model, that's a standard linear regression model, an OLS model, of income on the y-axis. There's a coefficient alpha, and then there's a beta, which is the coefficient on percent government employees, which is the independent variable. So we have a constant and the coefficient. We're going to estimate both alpha and beta. We can do so using using standard techniques. We saw earlier the equations. Typically, we use some kind of regression computational aid like R or theta. It produces this table. It has the coefficients for both the constant, which is the alpha hat, and for the percent government employees. It is in fact negative as we expected. It gives you standard error for each one of these coefficient estimates. We divide the coefficient by the standard error to get the t-value, which it gives to us helpfully over here. And we compare the t-value to the critical value to see if we have significant difference from 0. In this case, we have 7 data points and 2 parameters to fit. So the number of degrees of freedom are 7 minus 2, or 5. The critical value for the 95% confidence level for a two-tailed test is 2.57. 6 is greater than 2.57, and therefore we can say that percent government employees significantly affects per capita income, and reject the null hypothesis that there's no relationship at all at a 95% confidence level. Okay. But forget for a moment about hypothesis testing, and let's talk more about the predicted values. So we can see that the line we get is given by this bottom equation. This negative 1,000 or so is the slope of the line. You multiply the slope times x, and then you add to that the constant associated with that line. This is the best fit line through these 7 data points, which is obtained by minimizing the squared error around that line, of the data around that line. So this is y hat. Each of these y hats is a predicted value given a particular value of x and these coefficients. Note we don't have to only use values of x that we have in our data to do these predictions. We can use any value of x we want. This best fit line gives us not only predictions at the points in the data set for x, but all points across all x is possible. Of course, as you get further from the actual data, they probably get less accurate, but the point is the line is a line. It goes on forever in both directions. You can plug in whatever you want in for x and get a prediction for y. That's one useful thing about this kind of modeling. So here's the regression line in this case. It's a good line. As we saw before, this is a very strong negative relationship. And we see that the line is pretty good. The errors around the line are pretty small. We can calculate them. So in each case, the model makes a prediction based on plugging in the x's from the model, from our data, multiplying by the estimated coefficient beta hat, and adding the constant. And we get a series of predictions for every state's data. Those predictions can be subtracted from the true value to get residuals. The residuals are again the difference between the true value and the predicted value. And some of them are negative and some are positive because some of these things lie above the line and some lie below the line. Negative being below the line. So Alabama is below the line, so it's a negative residual. And we see that it's negative over here. So now we have residuals. What do we do with them? Well, we can use these residuals, these errors in prediction, to help us assess how well we fit our data with our model. When we talk about goodness of fit, that is what we're doing. We're trying to assess how well our model predicts the dependent variable. And we can use these residuals to actually figure out how well our model fits the data, what our goodness of fit is. The smaller residuals in general, the better the fit to the model. If all the residuals were 0, all the points would fit on the line exactly, and our model will be perfect. It will be a perfect fit. We don't usually have that, so instead we need measures of how well our model fits the data. We're going to consider 2. The first is called root mean squared error, or MSE, and the second is capital R squared, or just R squared. First, mean squared error. What is that? The root mean squared error is a measure of the typical deviations from the regression line. As before, if you want to get a typical deviation, we're going to start by squaring the actual residual. And in fact, the root mean squared error is going to look very similar to the normal measures of squared error. So first, we square each residual. That's u hat squared. Then we add them up for all data points. In this case, there's 7 of them, so we'll add all 7. And then, as before, we're going to divide by n minus some constant based on degrees of freedom that we lose. Here, there are 2 parameters. So we're going to take the number of data points minus 2. So 7 minus 2 in our case are 5. In general, you take the number of data points, n, and subtract the number of parameters, k, in your model. From bivariate regressions, again, you have 2 because you have a constant and a coefficient on your single independent variable. And if you're looking at the book, the custom witness is a little different from the book. But this is your equation for root mean squared error. And then you take a square root to turn it from being a variance, a squared error, to a root mean squared error, something along more the lines of a standard deviation. That's it. You can also write this by removing the u's and just writing explicitly y minus y hat. So this is a residual, the difference between the true value in the data and your predicted value. So these are prediction errors. You square them, you add them all up, you divide by n minus the number of parameters. You take the square root and you get a root mean squared error. What does it look like? For our example, you have, these are the residuals. These are the residuals squared. They're big because the residuals are big. The sum is large. You plug this in, the sum, you divide by 5, and the square root puts it back to a more manageable number, 1,000. What does that mean? Well, it means you have a root mean squared error of 1,000. On average, the model we estimated then is off by about 1,000 in predicting the per capita income in a state. Is that good? It kind of depends on what you want the model to do. The dependent variable in our case ranges between 24,000 and 30,000. So the question is that difference of 1,000 in error small given the range that it's in, right? The standard deviation in our dependent variable is 2,700 or so. So we actually have an error below the standard deviation in our data. So I would say we're doing a decent job of predicting, right? And you can see that from looking at the best fit line. We're pretty close in predicting, and we're closer than we would be by just randomly guessing if we didn't know anything at all about the state's government employee percentages, right? If we just had 7 values for the dependent variable and picked a state at random and just guessed, right, we're going to do worse in general than we would if we knew this model and the percent government employees for that state. So I think in general we are doing pretty well in this particular state. Sorry, I skipped ahead a few slides back. Okay, so that's mean squared error. It has a nice interpretation as sort of the average error in prediction. But we often see a different measure as well called R squared. R squared has another nice type of interpretation, which is R squared is the proportion of the variance in the dependent variable that our model explains. And it's nice because it ranges from 0 to 1. If your R squared is 0, you're explaining nothing from your model. 0, nothing. That's almost never the case, but you're explaining nothing. The variation in your independent variable or variables in your model is explaining no variation in your dependent variable. If R squared were 1, the variation in our model perfectly explains our variation in our dependent variable. So we understand everything about the variation in our dependent variable from the model, given our data. That's R squared of 1. In between, as we get closer to 1, we're doing a better job of predicting the dependent variable with our model. So R squared gives a nice, so whereas the root mean squared error requires a little more knowledge and context to interpret, R squared is more broadly interpretable across different cases without having to know details about your actual case, like what the standard errors are in your case, what the size of the variables are, and so on. R squared is normalized in a sense between 0 and 1, so it's in some senses easier to understand. Okay, how do we calculate it? Well, it's a little harder to calculate than the other one, but not much. R squared is the regression sum of squares divided by the total sum of squares. The regression sum of squares is the deviations in the mean, right, predicted by our model from the mean predicted by our model over the total deviations from the mean. Another way of writing the regression sum of squares is as the total sum of squares minus the residual sum of squares. So you take the total variance, effectively, the total error from the mean, and you subtract from that the residuals, the stuff you didn't explain. Right? And then you divide that by the total. So what you're effectively doing is taking all the variance in y, in the dependent variable y, you're subtracting the stuff that you failed to ever explain. And what's left over is the regression sum of squares. It's the variance you did explain. And you divide the variance you did explain by the total variance to get the proportion that you did explain. If you explained all the variance, then the regression sum of squares is equal to the total sum of squares. The residuals are 0. Your line exactly fits all your data points. And you have an R squared of 1. If you have explained nothing, the residuals are the same as the total variance, the total sum of squares. Your regression sum of squares is 0, and your R squared is 0, and you explain nothing. You can see that in the bottom equation. This term on the top left and also on the bottom is the total sum of squares. It's just each deviation of y from its mean squared and added up. That's the same as the definition of the total sum of squares we dealt with before last lecture. The second thing on the upper right here is the residuals squared. So you take the sum of the squared residuals, subtract them from the total sum of squares, and divide by the total sum of squares. If the sum of the squared residuals is high, R squared is going to be lower. If the sum of squared residuals is low, R squared is going to be higher. So that should be intuitive. It requires a little more calculation than the root mean squared error, but not too much. So we can calculate the total sum of squares like before. We subtract the mean of the dependent variable from all the observed values of the dependent variable. We square them and add them all up. Then we calculate a residual sum of squares as before by using our model to predict values of the dependent variable for every case. We calculate the residuals, and we square them and add them up, and put it all together. So here, we had already done, for example, the residual sum of squares. So now all we have to do is do the total sum of squares, which is going to be bigger always. So now here we get the total, we get each individual squared deviation. Right, here's a deviation, the sum of squared deviations, and we get a giant number. Here's our total sum of squares. Here's a residual sum of squares next underneath. We take the total minus residual to give us what's left over and divide by the total, and that gives us 0.88. That tells us our model explains 88% of the variation in the dependent variable, which is very, very high. Right, with just this one variable, we're explaining 88% of the variation in the dependent variable. Right, with one independent variable, we get 88% of the variation in the dependent variable, which means we've done a great job explaining. Right, we do a very good job in predicting, so our R squared gives us a sense of that, which is nice. Okay, is R squared all we want to know? No. For instance, R squared will get larger as you add more variables. Right, as you add more variables, even if they're only marginally useful in predicting, they'll still improve your prediction marginally, and that will improve your R squared marginally, right? So in theory, you could just add 1,000 variables and get a better R squared. But the problem is, the more variables you add, the harder it is to understand what your model says. It becomes harder to actually test any hypotheses because your number of parameters gets really large. You can't add more parameters anyway than you have data points because n minus k gets negative. So there are negatives associated with adding more variables, and typically what you'll see, often what you see in some of these statistical packages, they report mean squared error, they report R squared, and they also report something called adjusted R squared, which adjusts for the number of variables you have. In general, what to do depends on what purpose you want to use the model for. If you're just trying to predict the outcome as best as possible and you don't care why anything is happening the way it is, then using more variables and just throwing them all in there can be useful. If you're trying to understand the causal relationship between an independent variable and a dependent variable, so you know why things happen the way they do, then you often don't want to just throw in the kitchen sink type of approach, and you want to be more careful in what variables you include and limit them to ones that actually affect your primary dependent variable and independent variable. We care about R squared more in that context when we're looking at prediction more, and we care about R squared less in general overall when we're not looking at prediction. So that's it for lecture 2. We're going to conclude next module with a problem session in which we'll go over a couple of things that were more useful to go over with pictures, more pictures, and then do a couple of practice problems. Thank you very much.